Now let's continue what we started. Let's go to practice. Page 375, your book. Let's start with question number 2. Question number 2 says, you are designing a pendulum clock to have a period of what? Of 1 second. So, capital T is the period 1 second. Okay? How long should the pendulum be? The question asked about the length of the string. So we have to solve for L. Okay? Again, let's write the equation. T equal 2 pi square root L over G or AG. You want to solve for L, you have to square both sides. So T square equal 4 pi square L over G. Okay? L equal, as you see, it's G T square over 4 pi square. Okay? Now, L equals what? G is 9.8 or 9.81. T, 1 square over 4 pi square. And the answer is 9.8 divided by 4 equal. The answer is L equal 0.25 meter. So you need a string length of 0.25 meter. So you obtain a pendulum with a period of 1 second. Okay? Now let's go to a new question. As you see, question 3 is the same exactly as question 2. He is asking you again about the length of the cable or string. Now, let's go to question number 4. Question number 4 and okay, number 4. The goal of this question is to show how does the period depend on what? On the value of gravitational acceleration. Now, the question says, calculate the period and frequency. Period and frequency. So we have to find T and F. Okay? Of a 3.5 meter long pendulum. This is L. L, it's 3.50 meter. This is the length of the string of the pendulum. Okay? Now you have to do this at 3 different locations. A, at the North Pole. A, at the North Pole, where the gravitational acceleration, G, equals what? 9.832 meter per second squared. Okay? Now, again, we'll go to what? To the formula, to the equation. T equal 2 pi square root L over G or AG. 2 pi L is 3.5 over 9 now 0.832. And the answer will be the answer is T equal 3.75 seconds to 3 significant figures. This is the period of this pendulum at the North Pole. Okay? Now, how to calculate F frequency? F simply it's 1 over T, 1 over 3.75. And the answer is F equal 0.27 hertz. Okay, this is A. Okay, now let's go to B. B, again we have to P, you should find the period where in Chicago, where the gravitational acceleration at that location, 9g equal 9.803 meter per second squared. Okay? Again, t equal 2 pi square root of L, which is 3.5 meter, divided by 9.803. And the answer is 2 pi square root of 3.5 divided by 9.803. And the answer will be 3.754. It's a little bit greater than the first answer. As you see here, the difference in the value of G is very small. So G varies slightly on Earth's surface. Okay? But we conclude that as G increases, T, as G decreases, T increases, and vice versa. Now, what about F? F equal 1 over T, 1 over this, 754. So the answer is 0.266 hertz exactly. Okay? Again, we can use this formula to find either T or L over what? Or G. Okay? Now, let's move to a second type or a second example of a simple harmonic motion, which is mass spring system. Mass spring what? System. Okay? Now imagine a spring is laid horizontally on a frictionless surface, and this is the natural length of the spring. It's unstretched, uncompressed. Okay? So here x equals 0, which is the equilibrium position. Now, if we attach a mass to the spring, okay, we attach a mass. This is exactly x equals 0. Okay? Now what we will have, imagine someone is stretching the spring a distance of x from equilibrium position. This is x. This is the maximum distance, which is simply the amplitude of the motion. And then, if you release this mass, the mass spring system will start vibrating back and forth, left and right about the equilibrium position. Okay? Now, at this point we have maximum compression. So this is again, this is x, the amplitude in the other side. Okay? This is another example of a simple harmonic motion. It's the mass spring system. Now, how to calculate the period of this motion? Simply, this is the formula. T equal 2 pi square root of what? M over K. T equal 2 pi square root M over K. As you see from the equation, T depends on two factors. It depends on the mass and the spring constant of the spring. Okay? So, T depends on what? Depends on, number one, the mass, M. Number two, it depends on what? On the spring constant. Now the question is, how does the mass of a mass spring system affect the period of this motion? As you see, simply T is proportional again to square root of M. Okay? This is very similar to the case in the simple pendulum, where T equal 2 pi square root L over G. T is proportional to square root of L. But here instead of L we have what? The mass. Now, number two, K, spring constant of the spring, or sometimes it's called force constant. T is inversely proportional to what? To square root of K. Okay? Now, generally talking, as the mass increases, T also increases. But as K increases, T decreases. Again, how does this happen? For example, if the mass is quadrupled and increased 4 times, the period will be doubled because square root of 4 is 2. Okay? Now let's come to K. If the spring constant, for example, is changed by 9 times, increased 9 times. Instead of K, now it's 9K. This means the square root of 9 is 3. So T will become 1 over 3. T will increase by 3 times. Okay? That's all for the mass spring system. Okay, now let's go to again to the practice. Let's go to that. Practice. Page what? Page 377. 377. Okay? Question number 1. Okay? Now, question number 1. It says what? A mass of 0.30 kilogram. This is M. So M equal 0.30 kilogram is attached to a spring and is set into vibration with a period of what? T. T is 0.24 seconds. Okay? What is the spring constant of the spring? You are asked to find what? K. Spring constant. Okay? You can use the same formula again. T equal what? 2 pi square root of what? M over K. We have to solve for K. Simply by rearranging the formula. Step number 1, by squaring the 2 sides. So T squared equal 4 pi square M over K. We want to solve K. For K, K equals what? Equal what? 4 pi square M over T square. Okay? Now, K equals 4 pi square. M, the mass, it's 0.3. 0.3 divided by the period is 0.24 square. And the answer is 4. K is 206 Newton per meter. Okay?